All right, in this video, I am going to introduce the proof method, and we're going to be doing proofs for the rest of the semester. Yay. And depending on the kind of person you are, proofs can actually be a lot of fun. So in actual face-to-face classes, I get really giddy when we start doing proofs and when we solve proofs and things like that. Okay, so I'm going to share this screen here. All right. So as far as doing proofs, what we are doing is that we are showing that arguments are valid or invalid. So we're going to be doing both, what are called proofs, which show that an argument is valid, and we're also going to be doing refutations, which show that an argument is invalid, um, through the application of various logical rules. Okay, so and there's different ways of doing this. So with what's called standard natural deduction, which appears in most logic, introduction to logic textbooks, all you're doing is showing that the conclusions of arguments follow simply by applying rules. So with standard natural deduction, you actually don't make any assumptions. Now, what's good about standard natural deduction is it forces you to really get familiar with how the rules work. And various logic textbooks differ on which rules they include and which rules they do not include. But there's not really a set of exhaustive rules. So I've seen logic textbooks which would include as many as 50 um, different kinds of rules that can be applied to arguments. So it really just depends upon the author of the textbook concerning how many rules they want to include or don't include. Now, but the limitation of standard natural deduction is that you can't use natural deduction, standard natural deduction, to show that arguments are invalid. You can only use standard natural deduction to show that arguments are valid. Okay, so it's good to get familiar with the rules themselves, but you can't actually use those rules to prove invalidity. You can only use those rules to prove validity. Now, what's known as indirect proof, which I've already alluded to in the video on indirect truth table, this is what we're doing with the proof method. We are allowed to apply rules, and we're also allowed to make assumptions. Okay, so in particular, we are going to be assuming that the argument is invalid and then seeing if we can derive a contradiction from that assumption. Okay, and then actually the simplest method of proofs, which it involves the least amount of rules and things like that, is axiomatic deduction. So what you do with axiomatic deduction is you show that a valid argument is actually a theorem of a given logical system, and you can prove that a given valid argument is a theorem through the application of whatever that system's axioms are. Okay, so with axiomatic deduction, a lot of times the only symbols you're allowed to use are the tilde and the horseshoe. So we don't have any dots for conjunction or wedges for disjunction. We don't have triple bars. And usually the only rules you're allowed to use are modus ponens and modus tollens, and then the various axioms of the logical systems. Now, every rule of inference that we are using is actually itself a valid argument, is actually itself a theorem of propositional logic. So the rules that we're using can themselves be shown to be theorems of the propositional calculus that we're using here. Okay, it's by far the easiest way to do proofs, but it takes longer to learn. It's simpler because you're using less rules, so there's less stuff to remember. But since it's a little more complex in different ways, you have less to remember, but it also takes a little more time to learn, because you got to remember the axioms and how you if you're starting with an argument that's using symbols other than conditionals, other than the horseshoe or the an arrow, depending on what symbol you're using, you need to know how to be able to translate it and so on and so forth. So once you get more familiar with logic, axiomatic deduction makes more sense. But for an intro to logic class, axiomatic deduction is the obviously we're not doing that here. Okay, so just as any given logic book has sets of rules, these are the sets of rules that we are going to be using. So we'll start with the simplification rules. All right, so with rules of simplification, what this allows us to do is just reduce a complex, well-formed formula into simpler and hence usually easier to use well-formed formulas. So what we're doing here is just a lot of times we're just replacing one well-formed formula with something that it's logically equivalent to, or we're breaking up a well-formed formula into smaller pieces. Okay, so once again, we'll be using triangle and box to stand for any well-formed formula whatsoever. Okay, so where triangle and box stand for any well-formed formula whatsoever, if we are given triangle and box can join together, that conjunction can be broken up, right? Okay, so if you have triangle and box, some formula triangle and box, that can be simplified to just triangle. That can also be simplified to just box. So if triangle and box are true and joined together on one line in a proof, clearly you can separate them. Why? Because there's only one condition where a conjunctive statement is true, and that's when both parts are true. Okay. Now, I mentioned this one before, but this is basically De Morgan's rule. If you have a negation outside of a wedge, okay, so that means it's not the case that this disjunct is true. Well, that means that both parts of it are false. So if you have a tilde outside of a wedge, so in this case, if you have it's not the case that either triangle or box, that can be simplified to just not triangle. It can also be simplified to just not box, right? So if you have this on a line in a proof, you can simplify it on a subsequent line to either just not triangle or just not box, okay? Now, if you have a false conditional, so what does this mean? The one condition where a conditional statement is false is when you have a true antecedent and a false consequent. That's the one condition where a conditional statement is true. So if it's false that if triangle then box, you can simplify that to just triangle and just not box. So it's false that if triangle then box, well, that means that triangle is true and box is false. So you can simplify it to either one of those things. Okay, this is simply double negation here. Not triangle is simplified to just triangle. If not triangle is false, then triangle is true. You know, same with box. Okay. Now, I mentioned this before as well in a past video, but a triple bar is the conjunction of two conditionals. So if you've got a true triple bar, that can be simplified to just if triangle then box, and it can also be simplified to if box then triangle. So triangle if and only if box can be simplified to just if triangle then box. It can also be simplified to if box then triangle. So you know, triangle is an antecedent of box, and box is also an antecedent of triangle. Okay, and then if you have a false triple bar, okay, that can be simplified to either triangle or box, and it can also be simplified to it's not the case that triangle and box. Okay, so remember, the two conditions where a triple bar is false is when one part of it is true and the other part is false. Okay, so from that we know that either triangle or box are true, and it's also the case that both. Why, if they could both be true, then we would have a true triple bar rather than a false triple bar. So if you've got a tilde outside of a triple bar, you can simplify that to either triangle or box, and you can also simplify it to just it's not the case that triangle and box. Okay, so these are simplification rules. So we've got 1, 2, 3, 4, 5, 6 simplification rules. Okay, now next we have inference rules. Now with inference rules, you're not just taking something from one line and then simplifying it on a subsequent line. Okay, so inference rules involve inferences with 2 lines. Okay, so to apply a simplification rule, you can apply a simplification rule to a single line, but with inference rules, you need to apply that rule on 2 lines in the proof. Okay, now, so let's start with a false conjunct. All right, so if you know that a conjunct is false, in this case, you've got that it's false that triangle and box, and you also have on another line that triangle is true. So if on one line in a proof, you've got a false conjunct, and then on another line in the proof, you've got that 1/2 of that conjunct true, you can derive that the other half of the conjunct is false. Okay, so if you have, it's not the case that triangle and box, and you also have triangle. So you need both of those things in the proof in order to apply this rule. If you have both, it's not the case that triangle and box, and you also have box. You can derive not, and you also have box, you can derive not triangle. And if you have, it's not the case that triangle and box, and you have triangle, you can derive not box as well. So, but keep in mind, again, you need both of these things, right? You either need not triangle and box and triangle to derive not box, or you also need, it's not the case that triangle and box, and then you need box so you can derive not triangle. Okay, now this rule is, this is just a disjunctive syllogism, right? So if you have either triangle or box and you have not triangle, you can derive box, okay? And also if you have triangle or box and you have not box, you can derive triangle. So that's a simple disjunctive syllogism. Okay, and then our last 2 inference rules that we're using, these are modus ponens and modus tollens. We've already seen these, right? So modus ponens. If you have if triangle then box and you've got triangle, you can derive box. Likewise, if you have if triangle then box and you have not box, you can derive not triangle. Okay? So we've got 6 rules of simplification, and really we've only got 4 different rules of inference here, right? So we've got, you know, the false conjunct, where we've got that the conjunct is false and 1/2 of it is true. You can derive that the other half of it is false. We've got disjunctive syllogism, and we've got modus ponens and modus tollens. We're really only using 10 rules here. And again, this is not an exhaustive list of rules. Other rules that we're not using hypothetical syllogism. We're not using dilemmas, both constructive dilemma and destructive dilemma. We're not using tautology. We're not using distribution. We're not using associativity or commutativity. We're not using transposition. We're not using material implication or material equivalent. There's lots of different rules that we're not using here, okay? And that's fine. Now, so a lot of times a student will ask, well, I just did this in the proof. Am I allowed to do that? You know, is that a valid step? Okay, well, there's 2 questions here. Is it a valid step? A lot of time it is. Hypothetical syllogism, that is a valid rule of inference. But are you allowed to use it? No. Why? Because that's not a rule that we are using. So De Morgan's rule, you know, that's a valid rule, but it's you know, because De Morgan's rule also works with false conjuncts, aside from false disjuncts as well, but we're not using it for false conjuncts, right? So what I mean by that is if you have a tilde outside of a conjunct, you can distribute that tilde in the parentheses and change the conjunct to a disjunct, change the dot to a wedge. That's a valid rule, but it's not one that we are using here, okay? All right, now how to set up proofs. Okay, so the whole idea behind a proof is you want to show that the conclusion follows from the premises using the least amount of steps possible, okay? Now, but to move to a subsequent line in a proof, you either need to make an assumption on that line, or you need to show that a subsequent line can be logically derived from what you have on a previous line. So in order to move forward in a proof, you either need to make an assumption, or you need to show that something can be derived either using a rule of simplification or using a rule of inference. Those are the only 2 ways to move onto a subsequent line in a proof, okay? So first, as far as writing proofs, you list the premises vertically and number them, and then you put the therefore sign, this little dot pyramid before the conclusion, okay? Now, you then block off the conclusion. So when you block off the conclusion, what that shows is that that's what you're trying to prove. You know, so other ways of doing this on the first line, you could just write prove such and such, right? We're not doing that. Okay, now, and then after you put a bracket around the conclusion, you then indent the sequence. And on the next subsequent line, you make an assumption, okay? Now, your assumption is always going to be the opposite of the conclusion. So whatever your conclusion is, indent, and then your assumption, just throw a tilde in front of the conclusion, right? So since we're assuming that the argument is invalid, that is why we are assuming that the conclusion is false. So we've already got the premises stated as true by listing them vertically and numbering them. Okay, so we've got true premises, and then we're going to assume false conclusion. Okay, and then you use simplification rules and inference rules to derive conclusions on subsequent lines. So you show what's being derived, and then on the side, you justify it. You say which line or combination of lines you are able to derive that. Okay, now other textbooks have you also write the particular rule that you're using. You don't have to write the rule you're using, you just need to write the lines from which you are deriving that, okay? Now, this is just to avoid redundancy in the proof. Harry Gensler recommends that you put stars by lines that have been simplified, either by a rule of inference or a rule of simplification, simply to avoid redundancy in a proof, okay? So you don't want to solve a proof in 10 lines that can be solved in 5. If you take too many steps to solve a proof, you know, some of your steps are going to be redundant, where you're basically doing the same thing more than once, okay? Now, and then once you have derived a contradiction, you discharge the proof. So what does that mean? You lose an indent, right? You close. So when you indent, that shows that it's a hypothetical line of reasoning based on an assumption. When you lose the indent, when you discharge the proof, what you are doing is closing off that assumption, right? So when you lose an indent, what you are doing is you are closing off that assumption by contradiction. So once you discharge a assumption, in this case, it would be the main assumption, you state your original conclusion, and then you justify it by saying which lines contradict each other. So for example, here, 7 contradicts 9, okay? Now, and this is very important. Once an indented sequence is discharged, meaning if you've got a hypothetical line of reasoning which is based on an assumption, and you close that assumption by discharging the proof, right? You lose your indent on the next subsequent line. Let's say in this case, it's on line 10. You know, if you open an assumption on line 4 and then close off that assumption on line 10, you cannot use anything between lines 4 through 9 as a subsequent justification. So once you close, so if I had an indented sequence of line 4 through 9, which is based on an assumption. So I make my assumption on line 4, and then on line 9, I derive something which is contradictory somewhere in there. Once I discharge the proof on line 10, I can't use anything on lines 4, 5, 6, 7, 8, or 9 as a further justification. So once you close off an assumption, everything that you derived in that purely hypothetical line of reasoning cannot be used as a further justification. So if on line 11, I wanted to get something from line 5 and bring it down, I'm not able to do that. Why? Because that assumption is closed off. Okay, now, and just with indirect truth tables, with proofs, you can have multiple assumptions in the same proof. So there's no rule which says we're limited to a certain number of assumptions. Okay, now, but just as with indirect truth tables, every assumption needs to be closed off by contradiction, the same applies to proofs as well. So if you're doing a proof with multiple assumptions, you need to close off every single one of those assumptions by contradiction in order to prove that the argument is valid, right? So if I have 3 assumptions in my proof, I need 3 contradictions in my proof, all right? And they need to be closed off in order. So every time you make an assumption, you're going to get a new indented sequence, okay? So if in my first assumption, I make a secondary assumption, that would be another indented sequence. And then if I make a third assumption, that would be another indented sequence. Well, I can't close the first assumption unless I close the other 2 assumptions. They have to be closed off in order, okay? And in order to prove that an argument is valid, every single assumption must be closed. Every single assumption line must be closed off by contradiction. Now, what we're going to do when we do refutations, if an argument is invalid, it's going to have at least one open assumption. That is how you refute an argument, all right? So an invalid argument is one where we are not going to be able to close off every assumption by contradiction. Why? Because it's possible for the premises to be true and the conclusion false. So every invalid argument will have at least one open assumption. Every valid argument needs to have every assumption closed by contradiction, okay? All right, so let's go over some examples here. So to go over examples, I'm just gonna open examples on Logicola. Oh, I cannot minimize the recording while apparently you can't minimize a recording or minimize the video while you're recording, okay? So sit tight, I will get Logicola open here. All right, share screen. Okay, so there's the little guy on the bicycle. John Parsons was the last one to use Logicola. Is this you? Yes, it is me. And I don't want to use the keyboard. All right, let's go up here, load new exercise set. I'm gonna click on propositional proofs, all right? And we will start with easier ones that are valid, and let's turn off training wheels here. Okay, so notice what we have here. So we have our 2 premises, so premise 1 and premise 2, and then we've blocked out the conclusion here, all right? So this argument says, if not S, then not P. Premise 2 says it's not the case that either not P or G, okay? And then our conclusion is not G, and it's not the case that not E and not S, right? So if not S, then not P. It's not the case that not P or G, and our conclusion is not G, and it's not the case that not E and not S, okay? So my proof is going to begin on line 3, all right? And I am just going to assume that this conclusion is false. Make sure I type everything in correctly here. All right, okay. Now notice here, the main operator of my conclusion is this dot, okay? So that's why this tilde in my assumption needs to go outside of parentheses. So I'm negating everything in here, represented by this dot right here, okay? So there we go. Okay, now let's see what we have here. So this is my assumption, all right? And this is a tilde outside of a dot, so I can't do anything with this assumption line unless I know that either not G is true or this is true. Okay, so this can't be simplified on its own. I would need to apply a rule of inference here, not a rule of simplification. Okay, same with premise 1 here. So with premise 1, I can't do anything with premise 1. I would need to prove either not S or I would need to prove that not P is false, okay? Now here on line 2, I've got a tilde outside of a wedge, which tells me that these two things are both false, okay? Now, you can do a couple things here. Let's see what happens. So it's false that either not P or G. Well, from that I can get not P. All right, and Logicola just simplifies it to P. All right. Okay, now, and I can also get not G as well. All right. Okay, now where else do I have P being used? So here I have if not S is true, then not P is true. Okay, now but down here on line 4, I've got that P is true, which means not P is false. Okay, so I can actually get S by modus tollens of 1 and 4. So line 1 says if not S is true, then not P is true. Well, P is true, okay? But if P is true, that means not P is false. So by modus tollens, not S is false. So I can get S, okay? Now, and notice what I have here. Here I have that not G and, or it's not the case that not G and it's not the case that not E and not S, okay? So since I have that this half is true on line 5, so this is saying it's not the case that both of these are true. Well, on line 5, I've got that this half is true, not G is true. So that means that this other half, it's not the case that not E and not S is false, okay? So on line 7, I can derive not E and not S, okay? Now, and then this can just be simplified to not S, okay? Now, do I have a contradiction? Yes, I do. I have S on line 6, and then I have not S on line 8, okay? So I assumed my conclusion was false, and from that assumption, I'm able to get a contradiction. I have S on line 6, and I have not S on line 8, okay? So now I can close the proof. So I will close the proof by writing my original conclusion. Make sure I write it correctly, make sure I have all the parentheses and everything. Yes, I do. And this shows that the proof, or it shows that the argument is valid. Okay, so I assumed a false conclusion, and from that I was able to derive a contradiction. Okay, so then once I get a contradiction, I can close off the proof. I get not G, and it's not the case that not E and not S, right? Okay. All right, now with this one, here I have either not F or not U. Premise 2 is not P and not T. Premise 3 is if not T, then F, and my conclusion is it's not the case that if not P, then U. Okay, so what's next? Now, since my conclusion is already negated, I can just delete that tilde completely. I will assume it's, I will assume if not P, then U. Okay. Now, where else do I have P being used? Okay, I have it here on line 2. I have not P being conjoined with not T. Okay, well, that line can just be simplified to not P. Okay, and I can also just go ahead and simplify it to not T from 2 as well. Why? Because T is being used here, so I'll probably have to use that again. Okay, now, but with line 4 and 5, notice what I have. Here on line 4, I have if not P is true, then U is true. Well, on line 5, not P is true. So on line 7, I can derive U, okay? Now on line 3 here, I have if not t is true, then f is true. And I've got not t on line 6. So I can prove f is true. All right. Now, here with line 1, I can derive a contradiction in 2 different ways. I can derive a contradiction between u and not u. I can also derive a contradiction between f and not f. Okay, so this says either not f is true or not u is true. Okay, well, if f is true, that means not f is false. So I can derive not u, all right, from line 1 and line 8. Now, but notice what I have here. On line 7, I have u. On line 9, I have not u. All right, so I get my contradiction. So I will write out my original conclusion here and discharge the proof, and I've shown that the argument is valid. All right, so we assumed the opposite of the conclusion, and from that assumption we get a contradiction. All right, so this shows that the argument is valid. Okay. Now, I'm going to make things a little harder here, and hopefully Logicola will cooperate, because what are we supposed to do with multiple assumptions? Aha. Okay, here we go. All right, so premise 1, either G or E. Premise 2 says it's not the case that either not Y or not X and not, if not E, then not C. So it's not the case that both not Y or not X and if not E, then not C. And our conclusion is if not Y, then G. Okay? So hopefully this one will be a little more complex so we can make more than one assumption here. All right, so I'm going to throw a tilde in front of this conclusion. So my original conclusion is if not Y, then G. And my assumption will be it's not the case that if not Y, then G. Okay, now so here I have a tilde outside of a horseshoe. All right, so that tells me that the antecedent is true and the consequent is false, right? So if this horseshoe is false, that means the antecedent is true and the consequent is false. So from line 3, you can derive not Y. From line 3, you can also derive not G. Okay, now G is being disjoined with E up here. So here I have G or E, and down here on line 5, I have not G, right? So either G is true or E is true. Well, G is false. Well, that means E is true. Okay. So I've applied a rule to line 3. I've applied a rule to line 1, as indicated by the stars, and I've simplified everything that I can simplify. Line 2 cannot be simplified by anything. I don't have that this half is true or this half is true. So here I've got a tilde outside of a dot, and in order to break that up, I would need to have that either this half is true or this half is true. I don't have either one of those things. Okay. Now, so here's what I need to do. I need to make a further assumption. Okay. Now, so when you need to make a further assumption in a proof, what you want to do is break up a line that has a complex formula on it. So when you've got a complex formula on a line, which either cannot be simplified or you can't apply any rules of inference to it, you can make a further assumption to break up that line. Okay? All right. So I am going to assume, I'm just going to assume that this half of the conjunct is true. Now, and notice how it justifies it. Break line 2, right? Now, if you have multiple lines that you can break, just pick one, right? There's more than one way to solve a proof. There's more than one strategy to solving proofs. Okay, but here, the only line that I haven't broken up already is line 2. So I'm just going to assume that this half conjunct is true. I also could have assumed that that half of the conjunct was false. You can make any assumption you want to break up a line, but you want to assume something that's actually going to help you here. Okay, now, but how does this help us? Well, remember, here I've got a tilde outside of a dot. Okay, now if I assume 1/2 of that conjunct is true, given the fact that this tilde says they can't both be true, right? If I operate on the assumption that this half of it is true, that means I know that this half of it is false, okay? So it's not the case that either not y or not x, and if not e, then not c, and I've got either not y or not x on line 7, so I can derive it's not the case that if not e, then not c. Okay. Now, so Logicola did this automatically. This is double starred because this shows that we have another live assumption or another open assumption here. Okay, now, here I have a tilde outside of a horseshoe. So what does that tell me? That tells me that the antecedent is true and the consequent is false, okay? So from line 8, I can derive not e. So it's not the case that if not E, then not C. Well, that tells me that not E is true and C is false, or not C is false, okay? Now, but notice what I have here. I have E on line 6, and I have not E on line 9, okay? Now, but since I have two open assumptions, this contradiction closes the assumption that I made on line 7. It does not close my main assumption, okay? So since I assumed either not y or not x on line 7, it's from this assumption, the assumption on line 7, that I get a contradiction from line 6 and line 9, okay? So I am going to close off my secondary assumption. Whoops, there we go. So I assumed either not y or not x, and that led to a contradiction. Well, that means it's not the case that either not y or not x. Aha. Okay, now here I have a tilde outside of a wedge, which tells me that both of these things are false, okay? So if it's not the case that either not y or not x, from that I can just derive y from line 10. Now, but notice what I have up here on line 4. I have not y. So I've got not y on line 4. I've got y on line 11. Okay. So I can write out the original conclusion. If not y, then g. And I closed off my secondary assumption, and I've proven that this argument is valid. Okay, now notice the final justification here with when you close off assumptions. Okay, so we've got the from the original assumption line, in this case it's line 7, so from 7, and then the two lines that contradict. Okay, and then my final line in the proof, line 12, so this is from 3, where I made my first assumption, and 4 contradicts 11. Okay, so anytime you discharge an assumption, anytime you close off an assumption, you write the assumption line from 7 and then which two lines contradict. So on line 10, I justify it with from 7, 6 contradicts 9, and then on line 12, from 3, that's my original assumption line, and 4 contradicts 11. Okay? All right, I'll do one more here. Actually, that one looks too easy. That's not too bad. Okay, here we go. This one looks a little more complex. This one might actually need 3 assumptions. All right, so premise 1, not S. Premise 2, if C, then it's not the case that A only if not J. And line 3, premise 3, it's not the case that not both X and S and not C, and our conclusion is J. All right, so at least our conclusion is simple. So since our conclusion is J, I'm just going to assume not J. All right. Now, can I break anything up here? No, I can. No, I can. Right. So I have not S on line 1. Here, not J is a consequent of the conditional with A, but it's also part of the consequent of this conditional. All right. So I can't do anything here at all. All right. I can't break up what's in parentheses since, you know, it's bound by another operator. All right. So I already need to make a secondary assumption. Okay. So since C is being used both on line 2 and on line 3, I'm going to assume C. All right. And I'll do that to break line 2. Okay. So you could have assumed C to break up line 3 as well, but you know, I assumed that C is true. I could have also assumed that C was false, and that would have been fine to break up either one of these lines, right? Now, so here C is the antecedent of this conditional. So, and since I know that C is true, so if C, then it's not the case that A only if not J. Well, C is true, so it's not the case that A only if not J. So that follows from 2 and 5, and that is modus ponens, right? Okay, now, but here I have a tilde outside of a horseshoe, which tells me that the antecedent is true and the consequence, or the consequent is false, right? Well, if not J is false, that means J is true. That follows from 6. All right, so look what I have here. I assumed C, and I get a contradiction between line 4 and line 7, right? So that means I can derive not C from 5, and in this case 4 contradicts 7, right? So on line 4 we've got not J, and then on line 7 we've got J, right? So we can close off the assumption we made on line 5, okay? Now, but now notice what I have. I have, it's not the case that not X and S and not C. So again, I've got another tilde outside of a dot here. All right, and I've got that 1/2 of this conjunct is true, not C. Okay, well, if both of these can't be true, and I know that not C is true, I know that it's not the case that X and S, right, is false. Okay, so I can derive X and S from line 3 and 8. Okay. Now, and line 9 can be simplified, well, to just X. It can also be simplified to just S. Okay. Now, so now I have not S on line 1, and I have S on line 11, right? So my original assumption was not J, but that leads to a contradiction between line 1 and line 9, right? So I write my original conclusion, and I prove that the argument is valid. Okay, so here, this secondary assumption, C, was closed off from a contradiction on line 4 and on line 7. And then on line 12, my main assumption, not J, that I made on line 4, that is closed off because 1 contradicts 11. So I close off both assumptions, and by closing off both assumptions, I prove that the argument is valid. Okay. All right, isn't that fun? I think it is. You know, I'm weird like that. All right, we'll keep doing more proofs. We'll keep doing more practice. So please email me if you have any questions, and I will see you all soon.